Okay, let's read through all this information on the first page. So we're doing differential equations. A differential equation, or for short, you're going to write DE, saves you writing the words all the time, DE for short, is an equation that involves a derivative. Okay, makes sense. Differential equation, there's a derivative in the equation. So here are some examples of differential equations, and you can see them all in there. You can see all those dashes. There are sometimes first derivative, sometimes second derivative, sometimes first and second derivative. They're all different types of differential equations. The order of an equation is the highest derivative that occurs in the equation. So looking at those four examples up there, the first equation has just a y dash, so it's a first order differential equation. The second one has a first and a second, but the second is higher, so it's a second order. You get the point, right? Okay. An indefinite integral is equivalent to a differential equation because you're finding the integral of f of x. It means you're finding the solution. And we're going to spend a lot of time doing that. To test if a function is a solution to a differential equation, we substitute it in. We're also going to be doing that today. A family of solutions and particular solutions. The general solution of a differential equation normally involves one or more arbitrary constants, giving a family of solutions. So unless you're given some information, it could possibly represent a whole bunch of different types of curves. And if you're given information, you might be able to find the specific one. The number of arbitrary constants is normally equal to the degree of the differential equation. These constants can be evaluated to give particular solutions if one or more initial conditions or boundary conditions are known. So that's what I'm talking about, the information you have to be given. These conditions are usually points on the curve, but if higher derivatives occur, they may also involve the values of derivatives for particular values of x. A solution curve, which is the integral curve, may be just one of the connected branches of a function. The problem of finding a particular solution given the differential equation and suitable initial conditions is called the initial value problem. So you'll see the IVP in the textbook as well. It stands for initial value problem. Relations can be solutions of differential equations. Relations. So that's things that aren't necessarily one-to-one. Okay, relations that are not functions, so things like circles or, lots of other types of things, can be the solutions of differential equations with the usual arbitrary constants of familiar curves. And I'm also going to have to give you some rules to help you differentiate these things. Forming a differential equation from a relation that is not a function will involve the chain rule. That's the formulas I have to give you, but I'll give them to you when we get to those particular questions. A first order linear differential equation is a differential equation that can be put into the form y dash, so there's your derivative. So you'll have a derivative part at the front, and then you'll have a function of x multiplied by y is equal to a g of x. If it's in that form, then it is first order. An indefinite integral is equivalent to a first order linear differential equation. So the f of x is equal to 0, which means that y dash is equal to g of x. And the last one, an exponential growth differential equation is first order linear with g of x is equal to 0 and f of x is a constant. And that's the form of the differential equation that you'll see there. Okay, so the first type of question, we're going to do quite a few of these, is to test whether a given equation is a solution to a differential equation. So here is my differential equation up the top here, y dash is equal to 7y, and I'm going to test to see whether y equals 20e to the 7x is a solution to that differential equation. So I'm going to equate the left-hand side and the right-hand side to see if they're equal. I'm going to have to differentiate. Can you remember how to differentiate your exponentials? What is y dash? So you're doing the 7 times the 20 because the 7 from the top comes down. So it would be 140 e to the 7x, when the power of an exponential never changes, but when you differentiate, the 7 will come down the front. Now, to sub it in, it does, but let's show it. Okay, you can't just go, it does. So to sub it in, on the left-hand side of the highlighted yellow differential equation, that's equal to y dash. And we just worked out that y dash was equal to 140 e to the 7x. On the right-hand side of the differential equation, we are given 7y. Now, I don't want y in my equation. I'm going to substitute in that y is equal to the 20e to the 7x. So that's going to be 7 times 20e to the 7x, which does make the 140e to the 7x again. Because the left-hand side is equal to the right-hand side, so both of those things are the same, that means that that is a solution to the differential equation. So I just say, therefore, yes, it is a solution. Okay, let's do that process again for part B. But it's not just about the answer, it's about justifying it. So, same thing, let's differentiate. What is y dash for that differential equation? Minus 140, good, e to the negative 7x. So subbing into the differential equation, we're going to get left-hand side equals so the left-hand side was equal to y dash, so that was just the minus 140. And the right-hand side, which I know you're already working on, was the 7y. Y was just 20, e to the set minus 7x. So 7 times 20, e to the minus 7x. It is so close, but it's a positive. So they are not the same because one's positive, one's negative. So left-hand side is not equal to the right-hand side, which means it's not a solution. To go back from the derivative back to the equation, we are going to do that. Yeah, we are going to go back, but not yet. Let's wait. Question 2. Show that y is equal to tan x is a solution to the differential equation. So this is the same thing as what we just did, but involves trig. So just be careful when you're differentiating trig. Very easy to make mistakes. First of all, what is y dash? How do you differentiate tan x? Sec squared x. So sine over cos, and then you'd be integrating to a log. You can, but it's a lot more complicated. So differentiating tan, oh sorry, no, that would be integrating if we went to a log. You'd have to do a quotient rule, sorry, if you were doing, yeah, possibly would end up the same place, but it'd be a lot longer. So that is sec squared x. Don't mind the snacks as long as you're not being distracted by them. Not right now, but thank you. All right. No. Come on. Sub it into the differential equation. So we're doing the left-hand side and the right-hand side again. Left-hand side is y dash, which means I've just worked out that y dash is sec squared x. The right-hand side is 1 plus y squared. What is y squared? Y is tan, right? So Ben is super excited because he remembers this identity. 1 plus tan squared is indeed equal to sec squared, one of your Pythagorean identities. So left-hand side equals right-hand side, so therefore it's a solution. Question 3. Doing lots of examples here. Show that y equals ae to the x minus 1 is a solution. So now we're doing it with exponentials, more exponentials in there, but an extra constant, so a in the equation. First of all, differentiate it. What would y dash be equal to? a e to the x, that part doesn't change, and just the minus 1, correct. So into the differential equation. In the left-hand side, we have y dash, which we just worked out was a e to the x minus 1. Into the right-hand side, we have x plus y. X is going to stay there, but the y we replace with the y equation, which was a e to the x minus 1. And then the x minus x cancels out, and we get a e to the x minus 1, which was the same as the left-hand side. So therefore, it is a solution again. So I've shown that the left-hand side equals the right-hand side. So I subbed it into the y dash, subbed it into the x plus y, and got the same thing. No. Need more information.
Why did you stop the thingy when it was derivative? Because the y dash is a derivative. When you use the derivative, that's sort of the
equation was y dash equals x plus y.
Oh, okay.
So the left-hand side, yeah? Question 4. Show that, and this has a part A, B, C, D. Show that y equals sine of 7x and y is equal to cos of 7x. Both of them are going to satisfy the second order differential equation of y double dash equals minus 49y. So you might want to draw a little line down the middle because we have to do it for both equations. So first of all, starting with the y equals sine of 7x. I need to find the first derivative. Who can differentiate? 7 cos 7x. Excellent. Who can, I need a second derivative. Who can find the second derivative? Yes. So the 7 times 7, so you'll get the 49, but when you differentiate cos, it's negative. So negative 49, cos changes to sine of 7x. So was that, oh, the second side, you mean?
Yeah.
Oh, okay, see. All right. Now, rather than do a left-hand side equals right-hand side here is another option. This sine of 7x, where's my highlighter? There it is, sine of 7x, that is what y is equal to, correct? So let's just change that to be minus 49 and replace the sine 7x with the y, and then I have got the equation y double dash equals minus 49y. Well, just the different ways of doing it, and some equations, if you don't have the exact same thing, subbing it back in is not quite as nice. But with trig, it is a nice thing to do for trig questions. Let's try the other one. The second equation was y equals cos of 7x. Okay, differentiate it once. Okay, tell me please the derivative of cos 7x. Negative sine, keep going, Isaac. Sine of 7x. Good. Second derivative, someone else. Very good. Remember, you got all these on your sheet if you need to. No, it's not. Then let's do the same thing. The cos of 7x is the y that we started with. See up here, y is equal to cos 7x. So we can just say that that's equal to minus 49y. Guys, can we just concentrate, please? Part B. Show that y equals a sine 7x plus b cos 7x satisfies the differential equation for all values of a and b. Okay, that means we have to differentiate it twice. Who would like to have a turn? Can you please differentiate a sine 7x plus b cos 7x? All right, off you go, Ben. Wait. Yeah. Okay, so then the second derivative, is it positive or negative? Yep. Don't forget the B. Very good. Now, if I factorize out the negative 49, I get sine 7x minus and a minus, so plus. Oh, yeah, thank you. Thank you, yes. Plus b cos 7x. And then that part inside the brackets is the original y equals equation. So there it is, minus 49y again. So we've now proven 3 different equations that all work for that differential equation. Part C, find the value of the second derivative when y is equal to, I want to find the second derivative when y is equal to 5. Well, exactly. If that was the equation, all I have to do is sub in that the y is equal to 5, and we get negative 245. What transformation maps each solution of the differential equation to its second derivative? So this is a bit of an explain type of question, which I know we all love. Correct. So that's what I assume he meant by change of concavity. So we've gone from a maximum to a wrong way around. Yes, correct. Concave up to concave down. That's a better way to think of it, isn't it? Exactly. So the minus sign means that we've reflected the curve, and the minus means that we've made it 49 times steeper, exactly what they were saying. So, um, yeah, nothing. You could check. Yeah, no, we don't use the third derivative. Boys, can you write this down, please?
Oh, that actually makes sense. Ish, mate.
Right. Got that one? So question 5, a new type of question. It says to solve. We are now going to solve a differential equation given that we have a point at 2, 7. So to solve it means that we need to go back and find out what the original equation would have been, which means we have to find the indefinite integral. That was stuff I read out at the beginning. I know it's a bit of a blur when I read out all that information though. So if you have got y dash equals 2x, if you want to find y, it means you are integrating the 2x with respect to x. Integrating. You are now going between the two things, don't mix them up. What is the integral of 2x? Correct. Now, we've been given some information so that we can work out what the plus c part is. So we now sub the point 2, 7 into the equation. The y is equal to the 7, x is equal to 2, so 2 squared plus c. So 2 squared is 4, subtract the 4 from the 7, and we get that c is equal to 3. And our solution, we rewrite the equation for y, would be y equals x squared plus 3. We have found the original equation that solves that differential equation with the information that we have been given. Question 6. Example 3 showed that y equals ae to the x minus 1 is a solution to y dash equals x plus y. We remember that equation, hopefully, for all values of a. So we want to do a few more things. Find a particular solution passing through the origin. Okay, so if we already know what the equation for y equals there, we can just sub the origin, which is 0, 0, into the equation that I'm highlighting there in yellow. Okay, and we'll be able to find out what capital A is equal to. So that would be 0 equals a e to the power of 0, so that's just going to be equal to 1, because anything to the power of 0 is equal to 1, minus x, which is also 0, minus 1. So that just becomes a minus 1, or in other words, a is equal to 1. Not a lot of room here. Which means we can say that the solution to that equation would be y equals, instead of ae to the x, a is just 1, so it's e to the x minus 1. Now remember, this is actually representing kind of like a family of curves, because a could be different things, right? So now it says in part B, find another solution now if y equals negative 2 when x equals 0. And this is building up because right down, if you peek down at F, we're going to be drawing all these curves on a Cartesian plane. Okay, so this time we sub in x is 0, y is negative 2, and we're going to get another equation. So negative 2 equals ae to the 0 minus 0 minus 1. So that time we're going to get a is equal to, I'm going to move the 1 across the other side, so negative 1. And this one is y equals negative e to the x minus 1. Still with me? Okay, so part C, find the particular solution, new point again, at 0, negative 1. Okay, if we put negative 1 in there, we're going to get negative 1 equals ae to the 0 minus 1. What does a equal this time? 0. So that's actually kind of a special one, because that means the whole first term of your equation disappears, and you'll get y equals negative x minus 1, which is actually a straight line. All the other ones are obviously exponentials. Part D, analyze the gradient and concavities of the solutions in part A, B, and C, identifying any stationary points and points of inflection. That is a lot of stuff to do in such a small amount of space, but we're going to do it. So I'm going to do part A right over here on the left. I'm going to do A, B, and C. I'm going to divide it into 3 columns there. So the first equation for A was y equals e to the x minus 1. I need to find the gradient and concavities, find stationary points and points of inflection. Well, if I want to know the gradient, that means I need the derivative of that particular equation. Derivative of e to the x is e to the x. Derivative of x, the negative x there, is negative 1. Because I want concavities as well, while I'm differentiating, let's find the second derivative, which would be e to the x. Good. Okay, so what this tells me something. This e double derivative is e to the x. It means it's always going to be concave up, because it doesn't matter what value of x you put in there. Even if you put in something negative, it just means it's going to be very small, but it would still be positive, right? So this means the curve here is always concave up. Okay? Now, how would I find the stationary points? Which equals 0? The y dash. Good. So when y dash equals 0, we would get e to the x equals 1. How would I solve for x there? It will be 0 because e to the x equals e to the 0 is equal to 1. The powers must be equal, so that means x is equal to 0. If x is equal to 0 because I want a point, what would y be equal to? Sub x is 0 back into the very top line. E to the 0 is 1 minus 0 minus 1. It is 0. Yeah, we knew that from before. But now we know the turning point is at the origin. But yes, we did know that point went through the origin. Good point, Logan. I subbed it into that one, the y equation. Okay, technically we're supposed to identify the type of the stationary point or point of inflection. How, we probably know, but how, we do know. It's always concave up, right? So it's a minimum. If you're wanting to check it, you would sub it back into the second derivative if you didn't make that connection. You'd go the second derivative, when I sub x equals 0 into it, is e to the 0, which is equal to 1. And because that's greater than 0, that means I have a minimum at the origin. Okay, I think that covers everything for part A. We have to now have a look at part B. So part B has an equation y equals negative e to the x minus 1. So find the derivative. Y dash equals negative e to the x minus 1. And while we're at it, second derivative is negative e to the x. So just like in part A was always concave up, what's this one going to be? Always concave down. Not what we're doing right now.
Not too confusing.
So if we were, the other thing we look at here, what do you know about that first derivative?
It has no stationary point
Why do you know that?
because you can't have negative.
Yeah, so you would know if you, the e to the x part is always going to be positive because no matter what x you put in there, that's always positive. But with the minus sign in front of it, it means it's always negative, and the minus 1 still always negative. So there is no stationary point because we can't solve it, but we do know that that gradient is always negative, which means that the curve is going to be decreasing. So it's always decreasing. Okay, so that's probably, I don't need to show that there's no solution to that though, do I? We all understand that bit?
Yes.
Okay, so the last one then, we need part C, which is the easy one because it's a line. Y equals minus x minus 1. We know that it's linear. What's the gradient of that line? So the gradient is always equal to negative 1 because it's always in front of the x. There's no turning points to straight lines. Yes. No. There's no turning point at 0. The second derivative would be equal to 0 and there's no x value in there for you to solve for that. So there's no x value where you're going to have a turning point. This would also be decreasing all the time because it's a negative 1 gradient. So it's always decreasing. Yep. And there's no concavity and no turning point, which all things we've discussed. Okay, part E. By substituting that y dash is equal to 0 into the differential equation, identify the set of points where the solution curves have a 0 gradient. The differential equation is way back here. This is the one I'm talking about up here. The y dash equals x plus y. That was my original differential equation. So it says to sub in when y dash is equal to 0 into, I'll write it down there as a reminder, because if you're looking back at this, you might go, where am I subbing that again? I'm subbing into the y dash equals x plus y. So that means the 0 equals x plus y, or in other words, y is equal to negative x. Okay, so I have a solution to the curves at y is equal to negative x. We have to draw all of that. In part F, it says sketch the 3 curves of the differential equation and draw a dashed answer to part E. So there's actually 4 things I have to draw on here. All right, here we go. So we need a little bit of space below, but more space above.
Oh, I thought you were cutting it in half, so I did that squiggly like that. So, you're just doing a graph.
I'm drawing a graph. Okay. Let's maybe start with the straight lines because they're the easier ones. So the part E, y equals negative x, is going through the origin. It has a gradient of negative 1, which means negative 1 plus 1 there, or down there as well. And I want a dotted line. I'm actually going to rule it because this is going to get a little bit, this is going to be messy. This line is going to help me find the solution of curves. Yes, it's 45 degrees. The other straight line that I had was y is equal to negative x minus 1, which is the same gradient, but the y-intercept is negative 1. Gradient negative 1 still. So this one, this is a solid line. Okay, so they're the 2 lines that we've calculated. Now for the 2 curves. Part A. Look back, so I don't have to keep scrolling back, but look back to part D. For A, we found that there was a minimum turning point at the origin. So maybe I'll do a different color, green. So at the origin, there's my turning point. It's a minimum, so it's going to be going up from there. It's not a parabola though. Don't make it symmetrical. Exactly. Okay, so let's, just so we can see what is going on, if we were to sub in x is equal to 1, if x is equal to 1 into highlighted yellow A there, so e to the power of 1 is e minus 1 as a decimal. Isn't it just points, because it's 2.7 minus 2. So it's a 0.7. Yeah, you're close though. So it's just under the 1 mark. Okay, so what I'm typing in, this is what I'm doing. I'm doing e to the power of 1, and then I'm minusing 1, minusing the other one, because I'm subbing it in for the x, so there's the 0.7. If you wanted to, we could change that to be a 2 and a 2. So 4.3, if I went to 2, it'd be 1, 2, 3, 4.3, which is way up here. So my curve is coming up like that. If I went to, let's sub in a negative value, so keeping this in the calculator, that's going to change that to be a plus 1 there and a negative 1 there. So that is at 0.37. So that's about there. So not quite as steep, but it is coming up on that other side. And it actually won't, you can sub in more values if you want to make sure, it won't touch that red line. We've got one more to do. Part B. So B, we knew, is always decreasing. So what is the, let's sub in to the equation. Where's my equation up here? Let's sub in that x is equal to 0, so we can find a y-intercept. So I would have negative e, whoops, that's not e, negative e to the 0, then minus, yep, you're right, minus 0 minus 1, negative 2, sorry, there you go. Negative 2. You can sub in more values so you get some values on either side, but what is going to happen at negative 1 here, it gets quite close to the line, and it's kind of going to be approaching the red line as it comes up to the negative values here. But as you go further to the right, it's actually going to get really steep and come down that way and keep decreasing down there. Okay, so except for the dotted line, those three, the line in the middle and the two green ones, they are three different sets of curves that represent our differential equation depending on the value of A. No, it shouldn't be. It's not an asymptote. It just starts getting steeper that way. But yeah, I probably made it a bit too steep, to be honest. Let me redo that. It's not quite that steep. Kind of comes out here. But I just want to emphasize that it's moving further away. Part G, do all solution curves to this differential equation have a stationary point? We kind of already know that because we went hunting for them. No, they don't. The only one that did was equation A, but you can actually see that on your graph as well because it's the one that intersects with my dotted line. The solution to the differential equation, they intersected at that turning point, so it's only A that has that stationary point because we can see it there. So let's just write in there, where am I? Can I write it? I'm running out of the room. Only part A intersects with x plus y equals 0 and has a stationary point, SP for stationary point. The other curves do not intersect, which is why they do not have a stationary point, but I won't. SP for stationary point. Question 7. I know. We're not doing those today. Question 7. Differentiate the equation x squared plus y squared equals a squared. Yes, that is. But we're not doing that today. Yep. They're a little bit painful. Okay, this equation, when you look at that equation, you are thinking circle. A circle is a relation. How can I differentiate the whole equation when it's got both x's and y's in that equation and a constant as well? It's not irrelevant. So here is, and I'm not sure, have you advanced people done this? But anyway, we'll have a look. Here is a version of the chain rule to help you differentiate different types of equations. There's two of them here. If I want to differentiate d over dx, I want to differentiate something with a y squared in it. The problem in that I can differentiate the x squared, but how do you differentiate a y squared with respect to x, right? Chain rule is the heading. I'm about to give you a couple of formulas. Okay, so if I have an equation that has a y squared in it, and I want to differentiate the y squared, I'll write the formula down and then I'll explain how it works. It's d over dy of y squared times by dy over dx. Now, what is happening there is I want to differentiate. If I want to differentiate a y squared, I want to do a d over dy, right? I want to differentiate with respect to y. But I'm differentiating the equation with respect to x. So think of the cancelling out. The dy here and the dy there means I'm actually having a d over dx as a result of what I've done with that chain rule there. Now that's why it works. The shortcut that you're going to remember is that the derivative is always equal to, so you differentiate the y squared and you'll get 2y times y dash. Because y squared differentiates to 2y when you're differentiating with respect to y. So it's 2y times y dash. That's the rule. The other one that you need to know is how to differentiate with respect to x, an x and a y multiplied together. So let me again do the same thing. I'll write down.
Why did they do this? This is so cool.
Okay, now this d over dx. This is a product rule. What I'm doing is I am doing the u and the v, right? So the u is the x and the v is the y. And I need to do a product rule here. So in this first part, I'm leaving the y and I'm differentiating the x. Then plus from the product rule, leave the x and differentiate the y. That's the product rule, right? So that becomes y, because when you differentiate the x disappears, derivative of x is just 1. And so from that first part, you just get the y, right? Then to differentiate the second part, I've got dy over dx, which is a y dash, and I have an x sitting out the front, so it's x y dash. So you can either go through that whole process every time, or you can know these little rules to help you differentiate a y squared and an xy. Yes?
Would it change around like if it was y times x?
No.
But
Just means
it
it's
makes a difference rather than even factor.
Yes, if you add extra powers and things in there, yes, it is going to be different, but we're not going to be doing that. All right, let's go with our question so you don't drag on too long. Yes, right now. That's what this question's about. Question 7 is using these rules. A uses the first one, B uses the second one. So differentiate x squared plus y squared equals a squared of the circle with respect to x, given that little a is greater than 0. Show that each equation in the family of curves satisfies the differential equation, which is y dash equals minus x over y. What geometrical significance does this have? Wow, there's a lot of things we have to do here. All right, so first of all, differentiate. I need to differentiate that lovely relation up there. The x squared, it's d over dx for everything, right? I can differentiate the x squared to get 2x. But the y squared, using the rule that I've now gone too far, there it is. When you differentiate a y squared, what does it become? 2y y dash. So plus 2y y dash. What happens when you differentiate the a squared? A is a constant because it's like a radius in the circle. So it is equal to 0. It would disappear. Okay, so we would now know that the 2y dash is going to be equal to negative 2x, moving that across the other side. And that y dash would be equal to negative 2x over 2y. The 2, cancel out, and I get negative x over y. So this is good news because look up here, y dash equals negative x over y. I've shown that I've gotten to there. What does it all mean? Remember that this x squared plus y squared equals a squared, that is the equation of a circle centered on the origin. So here is my circle. I am given, sorry? Well, because of my overlapping part.
No, it just says better than Mr. Happy.
Oh. Oh, okay.
After this spin.
So I have a point. All right. I have a point over here that I'm going to give coordinates x, y, some random point on the edge of my circle. And that would mean if I were to draw a triangle in here, the x would be the distance across horizontally, and the y would be the height up there, right? X and y. Now, what is the gradient of my radius? The radius of that circle, that sloping line that I've just drawn, Correct. Y over X. Good job. Gradient of the radius is equal to, yep, just the rise over run, which is Y over X. Yep, the radius coming out from the center of that circle. What is the gradient of the tangent? Now I'm going to draw that. Wait, I can't spell it. Wait, the gradient. I was combining the words gradient and tangent. Gradient of the tangent. So if you were to draw a tangent to that point out here, what's the gradient of that tangent? That is the gradient of my curve. And the gradient of my curve I worked out was minus x over y. What do you notice about the gradient y over x and minus x over y? They are the negative reciprocals, which means they are perpendicular. We have just proven that the radius and the tangent of a circle are always perpendicular to each other. So that is the significance of what we've just done. Therefore, hence, the gradient no. All right, let's do something similar. We now have a second one. Sorry, I know somebody's still writing. It is. There can be. The trouble is, we don't know what's going to be in a HSC exam, and there's always some interesting ones. I don't even know that one yet because we will purchase that in and have a look at the options. You know. All right, part B. Differentiate the equation xy. Look, there it is. Xy equals a squared. We have an x and a y multiplied together, and we know we're going to have to differentiate it. So it says it's a rectangular hyperbola. We want to differentiate with respect to x. So differentiating using the rule that I gave you at the top of the page. So differentiating the xy, you guys look back up, what do you get? So the product rule, so you leave the y, differentiate the x, so it's y plus, leave the x, differentiate the y. Product rule. Differentiate the constant, what do you get? 0. So x, y dash would be equal to negative y, which means y dash is equal to negative y over x. That looks kind of almost familiar, but not quite. So the other one. Okay, please note, if x is on the bottom, that x cannot be equal to 0, which for a rectangular hyperbola is kind of important. Okay, a rectangular hyperbola looks like this, right? So again, we're finding some point on that curve. What would be the gradient of, let's start with the tangent. Gradient of the tangent. The gradient of the tangent to that curve is what I differentiated, right? So it is the negative y over x. What is the gradient of
X on Y.
what is the gradient of the normal? Yeah, x on y. So what is the gradient from the center? So gradient would be equal to y over x. Now, what do you notice about those two gradients? So there's one that way and there's one going that way. They're the same gradient, but one's positive, one's negative. And they would be making not equilateral, but isosceles. They make an isosceles triangle.
Oh, sorry.
Well, they could make a equilateral in very specific circumstances.
So we're going to call that the tangent and radius because it's the from the center to that, like a radius again. The center and radius form an isosceles triangle. With the x-axis. Okay, the last question is a little bit easier, but just a different type of question. So question 8, does everyone written that down, sorry? Yep. Question 8, classify these differential equations in terms of their order and whether they are linear. Back on the first page, this is a reminder, for something to be first order linear, it has to be able to be put into the form y dash plus f of x times y is equal to g of x. Okay? That is what it means for something to be linear. It's really the linear part that you're worried about with that. The first order just means highest derivative is degree 1, like 1, right? So you can see for part A there, the highest derivative is 1. So it is first order, but is it linear? That's the other part I have to answer. So let's see if we can rearrange it and try and get it into the right form. If we leave the y dash there and I move the y over x across to the other side, what I've actually got, there's my y dash, which is the first part. Then I have got, let's just say, a negative 1 over x. I have a function of x there times by a y. There's my function of y, or y, sorry, and that is equal to 0, which 0 could be a g of x. It could be a... Yeah, right? So that one does actually, it is something that I have written in the form y dash plus f of x y equals g of x. So that one does work. It is a first order and it is linear because I've been able to put it into the right form. Can I do that with the second one? Well, no, I guess is the correct answer. You know it's going to be a no. But what I could try, if you subtracted the whole thing across again, you're going to have a 1 over y, right? You can't have a 1 over y. It has to be a normal y, right? So the only option here is to multiply the y across the other side. So it's y times y dash is equal to x. Now, unfortunately, you can't have your y times your y dash. It needs to be a y dash plus then your y term with a function of x in front of it. Okay, so this one, no, unfortunately, there's no way of separating that into the right form. So therefore, it is first order, because we had that one derivative in there, but not linear, because we couldn't get it in the right form.
So first order
Or is when you have a derivative